Hello and welcome to Dove Biology, APES Lessons to Go. This is Unit 2, and in this video we'll be exploring biogeochemical cycles. It was the Greek dramatist Menander who said that all things come from the earth, and to the earth they all return. This is certainly true when we talk about matter. As with energy, matter can't be created or destroyed. This is governed by the law of conservation of matter. But unlike energy, which flows, matter cycles through ecosystems. In order to recycle matter, all ecosystems have decomposers, like bacteria and fungus, which are responsible for returning the matter back into the ecosystem so that they can come back in future generations of organisms. Now, it is the nutrients, which are the elements and compounds that organisms need to live, grow, and reproduce. You might recall from your biology courses that there were 6 really important elements that are found in most of the organic compounds that we find in living things. Those include carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. We use the acronym CHNOPS to remember that. Now, it is the biogeochemical cycles which move these substances through the air, water, soil, rock, and living organisms. Now, what's kind of cool about cycles is that they really connect the past, the present, and the future. The elements that were present today were present at the very beginning of time. So the carbon atoms that are in your skin might have been part of leaf. They might have even been part of dinosaur skin. The oxygen that you inhale could have been inhaled by Aristotle, or maybe it was inhaled by some hunter-gatherer 25,000 years ago. Now, as nutrients move through cycles, they're going to accumulate in some areas which are going to be called reservoirs or sinks. Now, these biogeochemical cycles are driven indirectly or directly by energy incoming from the sun as well as gravity. So as we continue with this video, we're going to be exploring the major biogeochemical cycles so we can see how those very important nutrients cycle into the living components of an ecosystem and through the abiotic or non-living components of an ecosystem. So the first cycle that we're going to explore is the carbon cycle. Carbon is an essential element for living things. It's the central element for all organic compounds. When we think of carbon, though, typically we think of it as carbon dioxide in the atmosphere, serving as a greenhouse gas, helping to regulate the Earth's temperature. The main components of the carbon cycle are the relationship between photosynthesis and cellular respiration. During photosynthesis, plants take in carbon dioxide and store it in their tissues as various carbohydrates. Then, as consumers consume those plants, they're able to release that carbon dioxide back into the atmosphere as a result of cellular respiration. Additionally, once these organisms die, more carbon will be released from their tissues through the process of decomposition. Another way that carbon is regulated from the atmosphere is through large bodies of water like the ocean. Carbon dioxide is absorbed through processes of diffusion into large bodies of water. Here, they'll be taken up by aquatic plants and also assimilated into the tissues and shells of many aquatic organisms. As they die, they help to build up sediments at the bottom of the ocean. In fact, it is the sediments that are our first major reservoir of carbon dioxide, and the ocean itself is the second largest reservoir of carbon dioxide. Now, unfortunately, humans have an impact on the overall carbon cycle. When we burn carbon-containing fuels like coal, oil, and gas, those emissions are responsible for putting excess carbon dioxide into the atmosphere. Additionally, poor forestry management and deforestation are removing those important trees that are responsible for pulling a lot of carbon dioxide out of the atmosphere. Now, the second cycle that we're going to look at is one that should be quite familiar to you, the water cycle. The water cycle is important because water is an essential compound for life. It does a lot of important things. For example, it can regulate temperatures of ecosystems, and it's a limiting reactant for photosynthesis. The driving force for the water cycle is going to be the sun. The energy from the sun heats liquid water into its vapor form, and it's going to evaporate from bodies of water on the surface. Additionally, we're going to see water evaporating from leaves through a process known as transpiration. Now, as the water rises up in the atmosphere, it's going to cool down and condense around different pieces of dust in the atmosphere and form clouds. As those clouds get full of water, eventually they're going to need to give up that water as a result of the pull of gravity, and that's going to lead to some precipitation of various forms. If the precipitation is rain, some of that water is going to reach the surface and simply run off. It'll run into streams and rivers and then fill up those depressions like lakes and ponds. Some water, though, will find its way into the earth, going through the little pores that are available in the soil and the rocks. This process is known as infiltration. Once in the ground, it's going to get into our groundwater sources, and then it moves. It actually percolates through the ground, flowing with elevation from high elevation to low elevation until perhaps it might reach surface water areas to allow for recharging of our surface water sources. Some of that groundwater is going to be pulled up by plants through the process of capillary action and then be used in photosynthesis. Now, once again, unfortunately, humans are having an impact on this cycle. One way that humans impact this cycle is by removing vegetation. Without vegetation, runoff is much faster, and the faster water moves, it can lead to erosion, which pulls sediments, and those sediments can find its way into surface water ways, and that surface water then is going to have a limited reservoir, and so it disrupts that component of the water cycle. Another way that we disrupt the water cycle is by building things, putting homes and paving over the land so that the water cannot infiltrate. We're creating these impervious surfaces so the groundwater cannot recharge. Another way that we impact the water cycle is by actually pulling too much water up as we use wells as a water source. And then anytime that we're building near bodies of water, there's a chance that we're going to get various types of pollutants that can actually go into those bodies of water, either on the surface or even get down into the groundwater, which again is also going to disrupt that overall water cycle. The next cycle that we're going to look at is probably the most complex cycle of them all, and this is the nitrogen cycle. Nitrogen is a very important element. It's a component of both proteins and nucleic acids, so DNA and RNA. Most of the nitrogen that exists actually exists in the atmosphere as nitrogen gas. Now, unfortunately, that's not very usable for living organisms, so we have to have a way to be able to access that and make it more usable. Some nitrogen is converted into a more usable form of nitrous oxide by electrical storms, lightning. But unfortunately, we don't have lightning all the time, and some areas don't have lightning storms. So we have to have another way to be able to access that nitrogen from the atmosphere. And this is the role of bacteria. We have soil bacteria that are responsible for fixing that nitrogen and pulling it in, converting it from atmospheric nitrogen into ammonia. Additionally, some plants actually have symbiotic bacteria that have infected their roots and are living together with those plants and fixing that nitrogen from the atmosphere, and we call that rhizobium bacteria. So in the soil also, we have some specialized aerobic bacteria that's then going to be able to convert that ammonia into nitrates and nitrites, which then can be absorbed or assimilated by our plants. Now, once the plants have the nitrogen in them, it can enter into the food chain and be passed to other organisms along each trophic level. Now, when these plants and animals die, they're going to decompose, and so they'll still have nitrogen-rich compounds in their tissues. So once again, bacteria will go to work, and they will remove those nitrogen compounds and produce ammonia. This decomposition and conversion of nitrogen is called ammonification. The ammonia and ammonium can eventually be absorbed by plants, or it might be returned to the atmosphere. In order to do that, we have to convert the ammonium and ammonia back into nitrates and nitrites, and that's done through the process of denitrification. So specialized bacteria will convert that ammonia and ammonium back into nitrates and nitrites, and then that way we can convert it back into nitrogen gas, which can go back up into the atmosphere to complete that cycle. Now, unfortunately, once again, humans are having a great impact on the nitrogen cycle. One way that it's impacting the nitrogen cycle is through the use of inorganic fertilizers. Because nitrogen needs to be fixed first before it can be used by plants, it's a limiting reactant in plant growth. So by utilizing inorganic fertilizers and applying that to our crops, we can actually have an increase in plant growth. Unfortunately, putting too much nitrogen on the ground or at the wrong times might lead to it actually running off and getting into aquatic ecosystems, where once again nitrogen is still a limiting factor. Here we'll have vast algae blooms, which then will limit photosynthesis for submerged aquatic vegetation. And then when those algae die, bacteria will decompose them and use up all the oxygen available for the life there, and possibly even creating dead zones. This process is called cultural eutrophication. Some of our fuels that we're using actually put nitrogen into the atmosphere. When that nitrogen gets into the atmosphere, it will react with water vapor to form nitric acid, which then can fall as acid precipitation. This acid rain, as it were, will then change the pH of local ecosystems, affecting organisms that can't live within that particular range of tolerance. The next cycle that we'll look at is the phosphorus cycle. Phosphorus is a component of nucleic acids like DNA and RNA, but also it is a major component of cell membranes, the phospholipid bilayer. One thing that's interesting about phosphorus is that it doesn't have a gaseous form, so it's found mostly in rocks as a phosphate. And so it's going to move slowly through the soil as a sedimentary cycle. Because it moves very slowly, it's very limited in the environment, and so it's a limiting factor for the growth of plants. So as plants are able to access it, they're going to absorb it and then assimilate that into their tissues and then pass that down the food chain. Some animals, like birds and bats, who obtain that phosphorus can return some of it back to the environment in their waste in the form of guano. Now, once all these animals and plants die, when they decompose, bacteria will break them down and return that phosphate back into the earth. Now, once again, humans are impacting the phosphate cycle, mostly once again because of inorganic fertilizers. Since phosphorus, like nitrogen, is a limiting factor for plants, we want to put excess, we'll mine it out of the earth and put excess onto our crops to see if we can make them grow better. But if we apply too much or at the wrong time, then those phosphates will actually get into those waterways and, like the nitrogen cycle, disrupt that natural cycle, leading to these dead zones in the water. Lastly but not leastly, we have our sulfur cycle. Sulfur exists both in the atmosphere and stored underground in rocks and minerals, including sulfate salts that will be buried deep in the ocean sediments. Sulfur typically enters the atmosphere naturally as hydrogen sulfide as the result of volcanic action, the anaerobic decomposition of organic materials. There's actually some algae that produce natural sulfides, dimethyl sulfide, into the atmosphere. Now, in the atmosphere, it's going to become sulfur trioxide. And then that sulfur trioxide may interact with water vapor that's in the atmosphere to create sulfuric acid, resulting in acid precipitation. So because of natural presence of sulfur, our water typically coming from the sky is slightly acidic with a pH of around 5. Where humans once again come into the mix is when they're adding excess sulfate into the atmosphere as a result of burning of fossil fuels and high sulfur coal. Too much sulfur in the atmosphere is going to make the pH go even lower, reducing the natural pH of our rain and wreaking havoc in different ecosystems as those organisms can't live within that particular range of tolerance. The cycling of matter is an essential process and the basis for one of the four principles of sustainability. The more we understand these cycles, the better we are able to limit our impact on them so that we can live more sustainably into the future.